Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. Ladies and gentlemen, welcome to this video about the basics or the fundamentals of the cooling and heating loads. Also, we're gonna talk about the psychometric chart, but not in details. So please, I recommend you these kind of videos for more details about the psychometric chart. Also, we're gonna cover the energy recovery wheels, but just an overview about it and the ventilation in tunnels. So let's get started. Here we have air conditioning psychrometrics. We have here the psychometric chart, and here the cooler air, and here the warmer air, and we have the relative humidity, and we have here the wet bulb saturation temperature, and the enthalpy and the humidity ratio, and also the specific volume. So the air conditioning psychrometrics in air conditioning systems, the air must undergo one or several of the following processes: cooling, heating, dehumidification, and humidification. So here the temperature control, and here the humidity control. Psychometrics can be used to predict changes in the environment when the amount of heat, air, or moisture in the air changes. Okay, so use of the psychometric analysis is also important to determine the volume flow rates of air to be pushed into the ducting system and the sizing of the measure system components. So the approaches to temperature control in an air conditioning system is achieved by passing the air through the cooling or heating coil, which may use any of the following approaches. Vary the temperature of air supplied to the space while keeping the air flow rate constant. This is the basic constant volume variable temperature approach. Or vary the airflow while keeping the temperature constant for air supplied to the space. This is the variable volume constant temperature approach. Or vary the airflow rate and change the temperature for air supplied to the space. This is the variable volume and temperature approach. Vary both the supplied air temperature and flow rate, where the airflow rate is varied down to a minimum value. Then energy input to reheat the coil is controlled to vary the supply air temperature. This is the variable volume reheat approach. Approach to humidity control. We have many things here. So humidity control in a conditioned space is done by controlling the amount of water vapor present in the air in the space. When relative humidity at the desired temperature set point is too high, dehumidification is required to reduce the amount of water vapor in the air for humidity control. And you can check out all these things by yourself in details. When you have here the air conditioning system design. In the designing air conditioning system, the first challenge is to understand the components that affect the building heat gain or heat loss. This process is called heating or cooling load estimation. So the reactive challenge is to design controlled processes to maintain the desired condition or state point within the occupied space. These are usually called the system processes that use psychometrics. So we have here estimating cooling and heating loads. Load estimates are the summation of the heat transfer elements into gains or out of losses out of the spaces of the building. Each heat transfer element is called load components, which can be assembled into one or three of three basic groups: external space loads, internal space loads, and system loads. To properly understand the workings of the various external, internal, and system load components, the following items need to be gathered from a set of plans, existing building surveys, or occupant interviews. The burn square footage and volume, orientation of the building, sun effects on surfaces, year-round weather data, design condition, heat transfer, use of the spaces within the building, offices, conference room, lab, data center, hours of operation, and so on. We have here many things. This is very important to make a good concept design to enter these things in early analysis program or the hand calculation. We have here the psychrometry definitions of the air. The basic definitions are used to describe air under various conditions. So the atmospheric air contains nitrogen, oxygen, carbon dioxide, water vapor, other gases, and miscellaneous contaminants such as dust, pollen, and smoke. This is the air we breathe and use for ventilation. Dry air exists when all of the contaminants and water vapor have been removed from atmospheric air. By volume, dry air contains about 78% nitrogen, 21% oxygen, and 1% other gases. Dry air is used as the reference in psychometrics, but the moist air is a mixture of the dry air and water vapor. So we have here the psychometric chart, and you can check out the videos on YouTube for more details about it, to see the temperature for the dry bulb and wet bulb, the enthalpy, relative humidity, and the absolute humidity or humidity ratio. Okay, and the dew point temperature indicates the temperature at which water will begin to condense out of moist air. When air is cooled, the relative humidity increases until saturation is reached and condensation occurs. Condensation occurs on surfaces which are at or below the dew point temperature, like this. And also we have the specific air volume and the vapor pressure. And here are some measurements and how can you measure the all of these things. Okay. Also, we have here for the heating purposes, the majority of air-conditioned buildings are offices or are used for similar indoor activities and are occupied intermittently. The heating system must bring them up to comfortable working conditions by the time work is due to start. So the heating must come into operation earlier to warm up the building. A large part of the heating load when operating in daytime will be for fresh or outside air, which is not needed before occupation, and the heat up time will be reduced if the fresh air supply can remain inoperative. For this time, the required warm-up time will vary with ambient conditions, being longer in cold weather and least in warm. Optimum start controllers are now in general use, which are programmed for the building warm-up characteristics and sense the inside and ambient conditions. So they then transduce the required startup period and set the heating plant going only when needed. This and the previous scheme will save fuel. Also here you can see that we have here the ambient temperature of the air. It is very cold, and here is the return air, and you can make a mixture, okay, to get the required high temperature. So here is the preheating of the outside air and mixing with return air process lines. So addition of moisture, methods of adding moisture to the airstream are difficult to control since a lot of water remains in the apparatus at the moment of switching off humidification. For this reason, the heat humidity or humidify reheat recycle, as shown in figure 24.12, is to be preferred. Let's see, we have here the preheating and humidification in winter process lines. Gentlemen, I'm gonna let you get this PDFs, this reference is very good for you, and you have to check out many things. Of course, I cannot make all things clear now, or I'm gonna just skim. So we have here the temperature, and we have here many processes. You can check it out by yourself. So let's continue. We have here the breathing, so cold, dry, and here is the heater and warm, dry, and here cool, wet, and here the H, and here the warm, humidified. Also, the outside air proportion, the high internal heat load of many modern buildings means that the comfort cooling may be needed even when the ambient is down to 10 Celsius or lower. Under these conditions, a high proportion of outside air can remove building heat and save refrigeration energy. This presupposes that the fresh air ducting and fan can provide more air. This outside air can be filtered. There are adequate automatic controls to admit this extra air only when wanted. Surplus air in the building can be extracted. Also, we have here the cooling and dehumidification and preventive coolers and many things. I'm not gonna talk about these details. Why? Because I wanna teach you how to understand these things by yourself, and it's very important for you. I'm just showing you the ideas. So let's go to the focus or the point of this video. We have here the cooling and heating load calculations, estimation of required cooling heating capacity. So the specific objectives of this chapter are to introduction to load calculations. Wait a minute. Okay. Differences between conventional cooling and heating load calculation methodologies, methods of estimating cooling and heating loads on buildings, such as our rules of thumb, semi-empirical methods, cooling load calculations using CLTD or CLF method, estimation of cooling capacity of the system, heating load calculations. You know that heating load calculations are not common in India or United Arab Emirates or the Middle East or the countries that are not like Finland or North America. You know this, so it's not common for the Arab engineers or the Indians to deal more or many times with heating loads. That's why we're gonna talk about it now. So at the end of the lecture, we have here this PDF is for the students. So you have to explain the difference between the conventional cooling and heating load calculations, and we have here many things. So introduction, as mentioned in the earlier chapters, heating and cooling load calculations are carried out to estimate the required capacity of heating and cooling systems, which can maintain the required conditions in the conditioned space. So, to estimate the required cooling or heating capacities, one has to have information regarding to design indoor and outdoor conditions. That's why in HAB we used these things for calculations. Specifications of the building, specifications of the conditioned space, such as the occupancy, activity level, various appliances, and the equipment used. We talked about all these kind of things when we talked about HAB. And any special requirements of the particular application. For comfort applications, the required indoor conditions are fixed by the criterion of thermal comfort, while for industrial or commercial applications, the required indoor conditions are fixed by the particular process being performed or the products being stored. Also, we have here a great video about human comfort. This video is very interesting. Also, standard and adaptive approach. per thermal comfort. Yes, this video is very interesting. Please watch it. Okay. So heating versus cooling load calculations, as the name implies, heating load calculations are carried out to estimate the heat loss from the building in winter so as to arrive at required heating capacities. Normally during winter months, the peak heating load occurs before sunrise, okay? And the outdoor conditions do not vary significantly throughout the winter season. In addition, internal heat sources such as occupants or appliances are beneficial as they compensate some of the heat losses. So it is very good to have many people, many appliances, many lighting. As a result, normally the heat load calculations are carried out assuming steady state conditions, no solar radiation, and steady outdoor conditions, and neglecting internal heat sources. This is a simple but conservative approach that leads to slight overestimation of the heating capacity. For more accurate estimation of heating loads, one has to take into the thermal capacity of the walls and the internal heat sources, which makes the problem more complicated. For estimating cooling loads, here one has to consider the unsteady state processes, as the peak cooling load occurs during the daytime and the outside conditions also vary significantly throughout the day due to solar radiation. In addition, all internal sources add on to the cooling loads, and neglecting them would lead to an underestimation of the required cooling capacity and the possibility of not being able to maintain the required indoor conditions. Thus, cooling load calculations are inherently more complicated, as it involves solving unsteady equations with unsteady boundary conditions and internal heat sources. For any building, there exists a balance point at which the solar radiation Q solar and internal heat generation rate Q internal exactly balance the heat losses from the building. So thus, from sensible heat balance equation at balanced conditions, we have this. So where UA is the product of the overall heat transfer coefficient and heat transfer area of the building, Tn is the required indoor temperature, and Tout is the outdoor temperature. From the above equation, we can here get the outside temperature at balanced condition. We have here this equation. So if the outdoor temperature is greater than the balanced outdoor temperature given by the above equation, when T out greater than T out balanced, then there is a need for cooling the building. On the other hand, when the outdoor temperature is less than the balanced outdoor temperature, T out lower than T out balanced, then there is a need for heating the building. When the outdoor temperature exactly equals the balanced outdoor temperature, when T out equals T out balanced, then there is no need for either cooling or heating. Just open the windows and do what you want. Okay, for residential buildings with fewer internal heat sources, the balanced outdoor temperature may vary from 10 to 18 Celsius. As discussed before, this means that if the balanced outdoor temperature is 18, then a cooling system is required when the outdoor temperature exceeds 18. This implies that buildings need cooling not only during summer but also during spring and fall as well. If the building is well insulated, and small U multiplied by A, and alternately loads are high, then from the energy balance equation 35.2, okay, the balanced outdoor temperature will reduce, leading to extended cooling season and shortened heating season. Thus, a smaller balanced outdoor temperature implies higher cooling requirements and smaller heating requirements, and vice versa. So for commercial buildings with large internal loads, note that this is for the residential buildings, and we have here for the commercial buildings with large internal loads and relatively smaller heat transfer areas, the balanced outdoor temperature can be also as low as 2 Celsius, implying a lengthy cooling season and a small heating season. If there are no internal heat sources, if the solar radiation is negligible, then from the heat balance equation, T out balance equal to Tn. This implies that if the outside temperature exceeds the required inside temperature, say 25 Celsius for comfort, then there is a need for cooling, otherwise there is a need for heating. Thus, depending upon the specific conditions of the building, the need for either cooling system or a heating system depends. This also implies a need for optimizing the building insulation depending upon outdoor conditions and building heat generation so that one can use during certain periods free cooling provided by environment without using any external cooling system. Gentlemen, you have to study these parameters or the parameters that affect your system just to get the optimum solution for your building. So we have here the methods of estimating cooling and heating load. Generally, heating and cooling load calculations involve a systematic stepwise procedure using which one can arrive at the required system capacity by taking into account all the building's energy flows. In practice, a variety of methods ranging from simple rules of thumb to complex transfer function methods are used in practice to arrive at the building loads. For example, typical rules of thumb methods for cooling loads specify the required cooling capacity based on the floor area or occupancy. Table 35.1 shows the typical data on required cooling capacities based on the floor area or application. Such rules of thumb are useful in preliminary estimation of the equipment size and cost. The main conceptual drawback of the rules of thumb methods in presumption that the building as designed will not make any difference. Thus, the rules for a badly designed building are typically the same as for a good design. So we have here this table, we have here the application, and we have the required cooling capacity and these things. So required cooling capacities for various applications based on the rules of thumb and more accurate load estimation methods. Maybe 1, 2, 0. More accurate load methods involve a combination of analytical methods and empirical results obtained from actual data. For example, the use of cooling load temperature difference (CLTD) for estimating the fabric heat gain and the use of the solar heat gain factor for estimating heat transfer through the fenestration. These methods are very widely used by air conditioning engineers as they yield reasonably accurate results, and estimations can be carried out manually in a relatively short time. Over the years, more accurate methods that require the use of computers have been developed for estimating cooling loads, like hourly analysis program and these kind of software programs. The transfer function method, since these methods are expensive and time consuming, they are generally used for estimating cooling loads of large commercial and institutional buildings. ASHRAE suggests different methods for estimating cooling and heating loads based on applications, such as for commercial residences and commercial buildings. So cooling load calculations, as mentioned before, load calculations involve a systematic and stepwise procedure that makes into account all the relevant building energy flows. The cooling load experienced by a building varies in magnitude from 0, no cooling required, to a maximum value. The design cooling load is a load near the maximum magnitude, but is not normally the maximum. Design cooling load takes into account all the loads experienced by a building under a specific set of assumed conditions. The assumptions behind design cooling load are as follows. So design outside conditions are selected from a long-term statistical database. The conditions will not necessarily represent any actual year, but are representative of the location of the building. Design data for outside conditions for various locations of the world have been collected and are available in tabular form in various handbooks. That's why, gentlemen, we have a library in HAB for the weather. We can select your country because this is very important. The load on the building due to solar radiation is estimated for the clear sky conditions. The building occupancy is assumed to be at full design capacity. All building equipment and appliances are considered to be operating at reasonably representative capacity. So the total building cooling load consists of heat transferred through the building envelope, walls, roof, floor, windows, doors, etc., and heat generated by occupants, equipment, and lights. The load due to heat transfer through the envelope is called the external load, while all other loads are called the internal loads. The percentage of the external versus internal load varies with building type, site climate, and building design. The total cooling load on any building consists of both sensible as well as latent load components. These things are calculated or can be calculated using hourly analysis program, as we all saw in the reports of HAB. The sensible load affects dry bulb temperature, while the latent load affects the moisture content of the conditioned space. Buildings may be classified as externally loaded and internally loaded. In externally loaded buildings, the cooling load on the building is mainly due to heat transfer between the surroundings and the internal conditioned space. Since the surrounding conditions are highly variable in any given day, the cooling load of an externally loaded building varies wildly. In internally loaded buildings, the cooling load is mainly due to internal heat generating sources such as occupants or appliances or processes. In general, the heat generation due to internal heat sources may remain fairly constant, and since the heat transfer from the variable surroundings is much less compared to the internal heat sources, the cooling load of an internally loaded building remains fairly constant. Obviously, from energy efficiency and economics point of view, and this is very important, gentlemen, the system design strategy for an externally loaded building should be different from an internally loaded building. Hence, prior knowledge of whether the building is externally loaded or internally loaded is essential for effective system design. So as mentioned before, we have here, as mentioned before, the total cooling load on a building consists of external as well as internal loads. The external loads consist of heat transfer by conduction through the building walls. That's why an hourly analysis program is very critical to get the construction of each wall and its orientation, north, south, east, west, roof, and these kind of things. We talked about all these things in details. So we have here the external loads and by conduction through the building walls, roof, floor, doors, heat transfer by radiation through fenestration, such as windows and skylights. We talked about skylights too. All these are sensible heat transfer. In addition to this, the external load also consists of heat transfer due to infiltration, which consists of both sensible as well as latent components. The heat transfer due to ventilation is not a load on the building, but a load on the system. So the various internal loads consist of sensible and latent heat transfer due to occupants, products, processes, and appliances. Sensible heat transfer due to lighting and other equipment. So we have here the various components that constitute the cooling load on a building. We have here solar radiation through fenestration, and solar radiation through opaque surfaces. We have here infiltration, internal heat sources, and heat transfer from ground. Estimation of cooling loads involves estimation of each of all above components, exactly like what we did in our analysis program. In the present chapter, the cooling load calculations are carried out based on the CLTD CLF method suggested by ASHRAE. So for more advanced methods such as TFM, the reader should refer to ASHRAE and other handbooks. The standards that you have, gentlemen, is very important for this kind of calculations. So the estimation of external loads, heat transfer through opaque surfaces. This is a sensible heat transfer process. The heat transfer rate through opaque surfaces such as walls, roof, floors, doors. We have here the UACLTD, okay, and U, the overall heat transfer coefficient, and the A is the heat transfer area of the surface on the side of the conditioned space. CLTD is the cooling load temperature difference. We do not use the CLTD for the heating loads, only for the cooling. For sunlight surfaces, CLTD has to be obtained from the CLTD tables as discussed in the previous chapter. Of course, I will not have the previous chapter, but you can get it from the references or the books, okay? So adjustment, you have to get this value from the tables. Adjustment to the values obtained from the table is needed if actual conditions are different from those based on which the CLTD tables are prepared. Of course, you have to know the CLTD if you need to modify thing or get anything more. Okay, you have to check out the accurate CLTD value and how you can use it. For surfaces which are not sunlight, I think. Sorry, it's not sunlight. Sorry, sunlit. So this is sunlit. Yes. Sunlit. Yes. Thanks, ma'am. For sunlit surfaces, and here for surfaces which are not sunlit or which have negligible thermal mass, such as doors, the CLTD value is simply equal to the temperature difference across the wall or the roof. For example, the external doors, the CLTD value is simply equal to the difference between the design outdoor and indoor dry temperature, okay? For interior air conditioned rooms surrounded by non-air conditioned spaces, the CLTD of the interior walls is equal to the temperature difference between the surrounding non-air conditioned space and the conditioned space. Obviously, if an air conditioned room is surrounded by other air conditioned rooms, with all of them at the same temperature, the CLTD values of the walls of the interior room will be 0. The estimation of CLTD values of floor and roof with false ceiling could be tricky. Why? For floors standing on ground, one has to use the temperature of the ground. One has to use the temperature of the ground for estimating CLTD. However, the ground temperature depends on the location and varies with time. So I actually suggest suitable temperature difference values for estimating heat transfer through ground. If the floor stands on a basement or on a roof of another room, then the CLTD values for the floor are the temperature difference across the floor, difference between the temperature of the basement or room below and the conditioned space. So ladies and gentlemen, you have to be careful, be very careful when you deal with these things. If you want to calculate these things by hand or using these equations. This discussion also holds good for roofs which have non-air conditioned rooms above them. For sunlit roofs with false ceiling, the U value may be obtained by assuming the false ceiling to be an airspace. However, the CLTD values obtained from the tables may not exactly fit the specific roof. Then, one has to use his judgment and select suitable CLTD values, and this is according to his experience, okay? So you can ask your senior engineer about this. And here the fenestration, heat transfer through the fenestration through the transparent surface such as a window includes heat transfer by conduction due to temperature difference across the window and heat transfer due to solar radiation through the window. The heat transfer through the window by convection is calculated using equation 35.3. This. Okay, with CLTD being equal to the temperature difference across the window and A equal to the across the window and A equal to the total area of the window. The heat transfer due to solar radiation through the window is given by his here is the unshaded multiplied by the SHGF maximum. So here the area exposed to the solar radiation, and here is the maximum solar heat gain factor and shading coefficient, respectively. Okay, CLF is the cooling load factor. As discussed in the previous chapter, okay, the unshaded area has to be obtained from the dimensions of the external shade and solar geometry. Okay, so SH, GF maximum, and SC are obtained from ASHRAE tables based on the orientation of the window, location, month of the year, and the type of the glass and internal shading device. That's why the undergraduate course we have learned these kind of details and how we can deal with it. So it is not recommended at all for the undergraduate students to use hourly analysis program or any software program, because you will not be able to know what are behind the scenes. Or the student must know these basics and how to deal with the tables. And it's pretty important for any engineer or any designer to know what the behind the scenes. Okay. And here the CLF accounts for the fact that all the radiant energy that enters the conditioned space at a particular time does not become a part of the cooling load instantly. As solar radiation enters the conditioned space, only a negligible portion of it is absorbed by the air particles in the conditioned space instantaneously, leading to a minute change in the temperature. Most of the radiation is first absorbed by the internal surfaces, which include ceiling, floor, internal walls, furniture. Due to the large but finite thermal capacity of the roof, floor, walls, their temperature increases slowly due to the absorption of the solar radiation. As the surface temperature increases, heat transfer takes place between these surfaces and the air in the conditioned space. Depending upon the thermal capacity of the wall and the outside temperature, some of the absorbed energy due to solar radiation may be conducted to the outer surface and may be lost to the outdoors. So only the fraction of the solar radiation that is transferred to the air in the conditioned space becomes a load on the building. Okay, the heat transferred to the outside is not a part of the cooling load. Thus, it can be seen that the radiation heat transfer introduces a time lag and also a decrement factor, depending upon the dynamic characteristics of the surfaces. Due to the time lag, the effect of radiation will be felt even when the source of radiation, in this case, the sun, is removed. Okay, the CLF values for various surfaces have been calculated as functions of solar time and orientation and are available in the form of tables in ASHRAE handbooks. Like this, we have here, according to the orientation, here the direction the sunlit window is facing. We have here also the time. Okay, you get the CLF factor for glass with internal shading and located in north latitudes. Also here, the infiltration consists of both sensible as well as latent components. The sensible heat transfer rate due to infiltration is given by this equation. We have here V dot is the infiltration rate, cubic meter per second, rho node and CPM are density and specific heat of the moist infiltrated air respectively. T node and Ti are the outdoor and indoor dry bulb temperatures. Also for the latent heat transfer rate due to the infiltration is given by this equation we have here in HFG is the latent heat of vaporization of water, W node and W out are the outdoor and the indoor humidity ratio respectively. So I discussed in the earlier chapter the infiltration rate depends upon several factors such as the tightness of the building that includes the walls, windows, doors, etc. and the prevailing wind speed and direction. As mentioned before, the infiltration rate is obtained by using either the air change method or the crack method. So here the infiltration method it is ACH multiplied by V divided by 3600 cubic meter per second, and ECH is the number of the air changes per hour, and V is the gross volume of the conditioned space in cubic meter. So normally the ACH value varies from 0.5 ACH for tight and well-sealed buildings to about 2 for loose and poorly sealed buildings. For modern buildings, the ACH value may be as low as 0.2 ACH. Thus, depending upon the age and the condition of the building, an appropriate ACH value has to be chosen, using which the infiltration rate can be calculated. So the infiltration rate by the crack method is given by AC delta P to the power n cubic meter per second. We name the effective leakage area of the cracks, and C is a flow coefficient which depends on the type of the crack and the nature of the flow in the crack. Delta P is the difference between the outside and the inside pressure, and then is an exponent whose value depends on the nature of the flow in the crack. The value of n varies from between 0.4 to 1, so n is greater or equal than 0.4 or lower or equal than 1. The pressure difference delta P arises due to the pressure difference due to the wind, pressure differences due to the stack effect, the pressure differences due to the building pressurizations. So you have to keep that in mind. So also we have here miscellaneous external loads in addition to the above loads. If the cooling coil has a positive bypass factor greater than 0, then some amount of ventilation air directly enters the conditioned space, in which case it becomes a part of the building cooling load. The sensible and latent heat transfer rates due to the bypassed ventilation air can be calculated using equations 35.5, this, and 35.6, this. Okay. So by replacing V dot with V dot ventilation bypass factor, where V dot vent is the ventilation, and here the V dot is V multiplied, I think, by bypass factor. In the ventilation rate, and the ppf is the bypass factor of the cooling coil. Also, in addition to this, sensible and latent heat transfer to the building also occurs due to the heat transfer and air leakage in the supply ducts. A safety factor is usually provided to account for this depending upon the specific details of the supply air ducts. And please, we talked about, remember that we talked about the safety factor on our enhanced program. So, gentlemen, you can take a chance to read these things also again by yourself. And we have here the estimation of internal loads. We have due to the occupants, number of people multiplied by the sensible heat gain per person multiplied by the CLF. It is similar, but that's used for the radiation heat transfer through the concentration. Thus, the sensible heat transfer to the conditioned space due to the occupants are given by this equation. Also, we have here a CLF factor. Okay. Also, table 35.3 shows typical values total heat gain from the occupants and also the sensible heat gain fraction. We have here total heat gain. We have here the sensible, the other fraction or the other. This is the total, and you can get the latent from this sensible heat gain fraction. That's why we need these things in HAB, and also you can get it by your hands. Okay, and here the Q latent by occupants, the number of people multiplied by latent heat gain per person. Also for lighting, the installed wattage multiplied by the usage factor multiplied by the ballast factor multiplied by the CLF. So the usage factor accounts for any lamps that are installed but are not switched on switched on at the time at which load calculations are performed. The ballast factor takes into account the load imposed by the ballasts used in fluorescent lights. A typical ballast factor value of 1.25 is taken for fluorescent lights, while it's equal to 1 for incandescent lamps. The values of CLF as a function of the number of hours after the lights are turned on, type of lighting fixtures, and the hours of operation of the lights are available in the form of tables in ASHRAE handbooks. Also, we talked about the appliances, and here we have the appliance installed wattage, and appliances used in the conditioned space may add both sensible as well as latent loads to the conditioned space. Again, the sensible load may be in the form of radiation or convection. Thus, the internal sensible load due to the equipment. Notice that this is the wattage of the heat, not the electric wattage. And we talked about the electrical wattage in the energy simulation, okay, for energy modeling, to get the electricity consumed, not the heat. Okay, so heat is used here. The installed wattage in heat, and multiplied by the usage factor multiplied by the CLF. Also, the latent is also installed wattage multiplied by the latent heat fraction. And here is the sensible load and latent load and total load. We talked about these things from the we got it from the ASHRAE standards. For the cooling capacity of the system, here, in order to find the required cooling capacity of the system, one has to take into account the sensible and latent loads due to ventilation, leakage losses, and the return air ducts, and heat added through the return air fan. So here, 35.2, for this figure, we have here the return fan, return duct losses, and we have here the air conditioned room, and we have here the supply fan, and here the cooling coil, and here the bypass. Okay, so the coil total equal sensible plus latent. So we have here a schematic of an air conditioning system with the cooling coil, supply and return ducts, ventilation, and fans. The cooling coil has a bypass factor X. Then the cooling load on the coil due to sensible heat transfer of the ventilated air is given by this equation. And the latent heat load on the coil due to the ventilation is given by this. Okay, so you can get what you want from this. And the load on the coil due to leakage in return air duct and due to return air fan, if there is leakage of air and heat from or to the return air duct, additional capacities has to be provided by the cooling coil to take care of this. The sensible heat transfer to the return duct due to the heat transfer from the surroundings to the return duct depends on the surface area of the duct that is exposed to the outside area exposed, and the amount of insulation and temperature difference between outdoor air and return. Also, the amount of sensible and latent heat transfer rates due to air leakage from or to the system depends on the effectiveness of the sealing provided and the condition of the outdoor air and return air. Since the load due to return air duct, including the return air fan, Q return duct, are not known a priori and initial value, as a fraction of total building cooling load is assumed and calculations are performed. Okay, so since the load due to return air duct, including the return air fan, are not known a priori and initial value, fraction of total building cooling load, so it is assumed and calculations are performed. This value is modified at the end by taking into account the actual leakage losses and return fan power consumption. Okay, so gentlemen, you have to guess something, you have to make an initial assumption. It is not easy to get everything accurate from the first time, and you have to get the catalogs. If you use a fan or a motor, you have to know these things, exactly like what we did in our LNS program. Now, the total sensible load on the coil is obtained by summing all the total sensible load on the building QSR, sensible load due to ventilation, and sensible load due to the return air duct and fan. So 1, 2, 3, and then you can get to the sensible. And similarly, for the latent, and here the required cooling capacity is the summation of the sensible and latent, and this is the total that we get from our analysis program just in one click, and you do not know what exactly happened. That's why you must know these fundamentals and check out the equations again, and again. So one can also calculate the sensible heat factor for the coil and draw the process line on the psychometric chart, like what we get from HAB, and find the required coil apparatus dew point from the above data are discussed in an earlier chapter. Okay, we have here also many things, and the heating load calculations. This is a very important point. As mentioned before, conventionally steady-state conditions are assumed for estimating the building heating loads, and the internal heat sources are neglected. Then the procedure for heating load calculations becomes fairly simple. One has to estimate only the sensible and latent heat losses from the building, walls, roof, ground, walls, doors due to the infiltration and ventilation. Equations similar to those used for cooling load calculations are used, with the difference that the CLTD values are simply replaced by the design temperature difference between the conditioned space and outdoors. We do not need CLTD here. Since the steady state is assumed, the required heating capacity of the system is equal to the total loss from the building. As already mentioned, by this method, the calculated heating system capacity will always be more than the actual required cooling capacity. However, the difference may not be very high as long as the internal heat generation is not very large, when the building is not internally loaded. However, when the internal heat generation rate is larger, or when the building has large thermal capacity with the possibility of storing solar energy during daytime, then using more rigorous unsteady approach by taking the internal heat sources into account yields significantly small capacities, and hence low initial costs. Hence, once again, depending on the specific case, one has to select a suitable and economically justifiable method for estimating heating loads. So, gentlemen, you will follow the same procedure here, all these equations, but notice that the internal load, heating loads from the appliances, people, and lighting will help you. If you calculate it, it will help you to decrease the heating load. Why? Because they help you. Okay. So the same procedure, and no problem with this. Also, we have a strategy guideline, accurate heating and cooling load estimations. We have here the peak heating load. The peak heating load represents the amount of the heat loss to the outdoor environment at design outdoor and indoor conditions, which must be made up by the HVAC system to maintain the occupant comfort. Okay, so it's during the night. Okay, but the cooling loads during the daylight. So this is it's the same procedure. We have here the winter comfort zone. So this is in the space dry bulb temperature in Fahrenheit, and we have here this. So this is the ASHRAE winter and summer comfort zones. You can check them out also from ASHRAE. We have here the building orientation and many things that you have to check out. And here are the space temperatures and the comfort of humidity control So the final thing or the last thing that I wanna show you is when we talk about the heating loads, notice that you can, for example, the occupants or the heat from the occupants, it will be positive, but the heat loss from the walls and the glass will be negative. Why? Because we lose heat by the glasses and walls, but we add heat to the system from the appliances, lighting, and these kind of things. Then you can add all these things using the appropriate sign, positive, 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 or negative, and add them, and you get the total heating load. But of course, for the cooling loads, it's always positive. Okay, have the same sign. Okay, now gentlemen, we're gonna talk about the last thing here is the ventilation in tunnels and the energy recovery. I'm gonna show you just an overview about them, and you can get some books and videos to check them out in details. And also I have to confirm that or assure on that using preheaters and afterheaters enhances the heating loads or these kind of systems if required, and also the lighting and the occupancy or the appliances if they are too much, or if it helps you, if they help you in the heating or add heating heat to the system, this decreases the amount of air that's required for ventilation due to the equation that we talked about. We have here the equations that here the ventilation. Okay, so you notice that we have here the delta T. So if you do not have lightings or appliances, the required ventilation will increase. Okay. So now many buildings require substantial amounts of outside air to be brought in through their ventilation systems. In many cases, it is code or schools, and in other cases, it continues make up air for contaminated exhaust air laboratories. Regardless, exhausting expensive conditioned indoor air and replacing it with outdoor air is really expensive. So energy recovery devices like the enthalpy wheel can be incorporated in the design to transfer outgoing temperature and humidity energy to the incoming outdoor air. For the application, most energy recovery devices transfer heat sensible energy only. An enthalpy wheel allows both heat energy and moisture energy to be exchanged. The enthalpy wheels are usually made of porous materials to increase surface area, which aids in energy transfer. In most cases, a matrix core material is coated with a desiccant such as silica gel or other molecular sieves to increase latent transfer. The enthalpy wheel coated with a decent material is rotated between the incoming fresh air and the exhaust air. Heat and moisture are given up to the wheel, and when the space is in the heating mode, the heat and desirable humidity is used to precondition the incoming cold dry air. In the cooling mode, the incoming air is pre-cooled and dehumidified. So cause the cost to remove moisture can represent 30 or to 50% of the cost to condition air. Substantial additional savings are available with enthalpy wheels over conventional air-to-air exchangers. So we have here typical of energy exchange through an enthalpy wheel. We have here the supply air and we have here the outdoor air. We have here the return air at different temperature, and we have here the exhaust air at different temperature. Here for the summer, but here for the winter, we have here the outdoor is colder, and here the supply air, then the return air another degree, and then we have here the exhaust air. So here is the wheel. Okay, please, I'm not gonna talk about this kind of things in more detail. Why? Because I wanna you to get information by yourself from YouTube and read the catalogs and how does this thing work. This is really important and critical for everyone to try to understand something by yourself, and then you can teach the others. Okay, so now we have here the ventilation in tunnels, types of ventilation system in tunnel construction. There are various types of ventilation systems in tunnel construction provided to remove dust and poisonous gas during its construction and operation. So these ventilation systems in tunnel construction are discussed in this article. So the tunnel construction works are mainly carried out by drill and blast method, which have many safety and health issues due to the emission of dust and many poisonous gases. Hence, it is essential to provide ventilation systems in the tunnel during construction. So the main objectives of providing ventilation systems in tunnel are to provide the working crew an environment of fresh air, to exhaust out fumes and gases that is injurious to health and explosive in nature, to remove the drilling, mucking, and blasting gases emitted. So ventilation during construction and after completion of tunnel construction is an essential feature that a tunnel should own to facilitate functional, comfortable, and a safe tunnel environment for both the road and the railway tunnels. So we have here a good picture for this. So why ventilation system tunnel construction required? When the work is being carried out within the tunnel, each worker has to be supplied with 200 CFT to 500 CFT of fresh air constantly. The concentration of compressed air emitted during drilling purpose is contaminated with oil and dust, so this should not be taken as a source of air to play the role of ventilation. After each explosion, the face is completely covered with air that is full of fumes and dust, which is unfit for breathing. Before he starts to remove the debris of the explosion, the foul is surrounding him. The foul air surrounding him must be removed out by any source of exhaustion and get him fresh air. So here are the mainly three factors. So the length of the tunnel and its size, and the amount of explosives used for blasting and their respective frequencies, the condition and rate of temperature and humidity inside the tunnel. Working environment inside the tunnel. The working environment inside the tunnel is contributed by the following factors: the dust and gases emitted by the tunneling operations, exhaust gases emitted by the diesel operations, explosive or organic solvent emitted poisonous gases, for example, nitrogen oxide, hydrogen sulfide, sulfurous acid gas, carbon monoxide, flammable gases or oxygen shortage gas in the ground, for example, methane, carbon monoxide, and hydrogen sulfide. So we have here the density, also high temperature and humidity factors. We have here density of dust emitted due to the tunneling works, and we have here table 2 volume of generated poisonous gas in tunnels. You have to study these things to know the amount of air that's required to remove these contaminants and these poisonous things. Post tunneling works safety and health to secure safer and healthier environment during the tunneling works, it is necessary to take absolute measures while carrying out the operations of drilling, blasting, excavation, shot creating. We have here short creating. So it's shot creating. Okay, and mucking. Sawdust and smoke and poisonous gases inside tunnel can be removed efficiently with the help of a proper ventilation. So the government has considered this step to be safeguard the health and safety of labor working in the tunnel. I think this is the American government, but I'm not sure. Types of ventilation systems in tunnel construction. So the methods employed for tunnel ventilation generally depends upon the normal, emergency, or congested operation that will be dependent on the actual conditions of the size, cross section, traffic conditions, intermediate ventilation shafts, etc. Also, we have here types of ventilation airflow system in tunnels. We have here longitudinal ventilation airflow system in tunnels. Here, the direction of the airflow is longitudinal in nature at the beginning of the tunnel or the tunnel section starting. This moves the pollutant gases and influence that is followed by the fresh air. Then at the end of the tunnel portal or at the tunnel section end, the polluted air is discharged. So we have here a picture of this. Also, we have here the transverse airflow ventilation system in tunnel. We have here uniform distribution of fresh air is created along the length of the tunnel. It is mainly employed in road tunnels. Occasionally, it is used for transit tunnels. Consistent level of temperature and the pollutants will be maintained if this system is employed. The system can be either fully or semi-transverse. So you can check out the other details by yourself. Also, we have here therefore consistent natural ventilation system in tunnels. Also, you can get books about ventilation in tunnels because it's not easy to cover all these kind of things in one video. So mechanical ventilation systems in tunnels, we have blowing, exhausting, combustion of blowing and exhausting. Mechanical ventilation system employs mechanical devices like electric fans, exhaust, and blowers, which serves the function of removing the exhaust gases within the tunnel and helping blowing fresh air into the tunnel. Now, whatever be the device employed there, there are three main services that can be provided. Okay, and here blowing ventilation and exhausting ventilation and the combination of blowing and exhausting. You can check out all these kind of things by yourself also. Also, we have here dust prevention and tunnel construction. You have to prevent the dust and dust accumulation within the tunnel is the after effect of conduction, the blasting, drilling, mucking operations. The dust accumulated amount is beyond the permissible limit. It creates harmful effects for the people working and to the surrounding environment. The blasting of rocks as a part of tunneling operation will emit a high amount of silica in the environment. So the intake of same will cause a disease called the silicosis, which is fatal. Also, the dust control methods in tunnels, the methods used in control dust accumulation are wet drilling, use of vacuum hood, use of respirators. So now modern drilling machines are available that make use of water to drill. Here, the area that is to be bored is made wet, resulting in a reduction of dust emission. The figure below, let's see the figures. Okay, it shows a vacuum hood that is used in tunneling work. So you can jump and get or find out by yourself more about this kind of thing. We have here tunnel engineering features, advantages, and methods of tunneling in construction, tunneling surveying, methods of procedures, tunnel surveying. You have also can get many tunnel ventilation and for HVAC. can get many things here. Also can create PDF, can get. Please check out all these kind of things for more details, and also try to know how you can calculate the things based on the HVAC systems or calculations that we have just talked about. Okay, ladies and gentlemen, I think that is a good start for you to know the fundamentals, and of course, you, the details are, do not stop, or the details are uh, details are so wide and huge details. So I hope this video helps you to understand something that's related to the heating and cooling and the strategy of the HVAC calculations, and try to get box. Okay, and here's the refrigeration and air conditioning by this third edition by A.R. Trott and T. Welsh. And here is this lecture. Okay, and the strategy guidelines. And here are the air conditioning psychrometrics. You can get these things. Also, here are examples. You can check it out by yourself, of course, and you can check more and more on YouTube. Of course, I cannot cover all these data in one video. And these are the fundamentals. You know the fundamentals. We we studied the fundamentals at college, so you can just make a refreshment for yourself. Thank you very much, gentlemen, and I hope this helps you. Wassalamu alaikum warahmatullahi wabarakatuh.